Hello, AP Chemistry. This is Mr. Coker, and this is our last chapter of the first semester, Chapter 10, Liquids and Solids. You can find it in the Zumdahl textbook. Before we get into liquids and solids, just a little bit about a substance that we know occurs in liquid, gas, and solid form here on Earth, water. We've already studied gases. In this chapter, we're going to look at liquids and solids, and the solid and liquid states of water are very interesting. Now, solids and liquids are going to be condensed states of matter. Gases are considered an expanded state of matter, so all that means is that the molecules in liquids and solids are very close together. And they're going to have more order than gases, and they're also going to be packed in closer. Liquids are a little more disordered. They're fluid, which means the particles can slide past each other. But like gases, they are disordered and fluid, but they're more dense like solids. So liquids are very interesting because they're sort of in between gases and solids. They have some of the disorder of gases, but some of the density and packing of solids. Now, if we compare the heat of fusion for water and the heat of vaporization for water, sorry about the misprint on the slide here, that second one should say delta H naught of vaporization. The heat of fusion of water is 6.02 kilojoules per mole, and the heat of vaporization of water is 40.7 kilojoules per mole. So what it tells us is that when ice melts, some of the bonds between the water molecules, some of the intermolecular forces break, but even more break when liquid forms gas. In other words, when water evaporates or boils, you get 40.7 compared to 6.02. So it's telling us that there are a lot more of the attractive forces broken during vaporization than broken during melting. So it's kind of helps us understand that liquids are very similar to solids and maybe closer to solids than they are to gases. They're both condensed states. Water's density is 0.9971 grams per cubic centimeter at room temperature and pressure. So we usually round that off to 1. In fact, water is only has a density of 1 at, I believe it's 4 degrees Celsius. That it's actually at density of exactly 1. If you raise the pressure to 1,065 atmospheres, which is a really high pressure, water's density only goes up to 1.046. So that's telling you liquid water is already packed about as tightly as it can be. We're going to talk about the intermolecular forces, which are the important forces in liquids and some solids, but many of our liquids are held together by intermolecular forces. It's important that we know the difference between intermolecular forces, the forces between one molecule and another, and intramolecular forces, which would be the covalent bonds within the molecule. Chemical bonds are intramolecular, not to be confused with intermolecular forces. So in molecular solids, and a molecular solid would be something that is in the solid state, but at the smallest level is actually molecules, something like ice. Ice is molecules of water held together in a crystal, so it's a molecular solid. Sugar, molecules of sugar held together in a solid state in little crystals of glucose or sucrose would be an example of a molecular solid. In molecular solids, the forces between the molecules can be broken and formed more easily than breaking and forming the intramolecular forces like chemical bonds. So these easily broken and formed ones are the intermolecular forces. Typically in a diagram like the ones down below on the left and the middle, you would show intermolecular forces as dashed lines, not as straight lines like we do in Lewis structures for covalent bonds. One form of intermolecular force is called a dipole-dipole. Those would be attractions between any two polar molecules. If you have polar molecules, they're naturally going to rotate themselves to to be in an alignment so that the partial positive of one is going to be attracted to the partial negative of the other. Dipole-dipole forces usually are about 1% of the strength of a typical covalent or ionic bond. It's actually a little higher for something called a hydrogen bond. Hydrogen bonds are kind of a particularly strong version of dipole-dipole force. You get this when you have hydrogen attached to nitrogen, oxygen, or fluorine. Now the reason why NH, OH, or FH gives you the ability to hydrogen bond between molecules is, first of all, hydrogen, nitrogen, oxygen, and fluorine are very small, which allows very close approach. So Coulomb's law tells us the closer things are, the more they're attracted. Also, there's a high degree of polarity. N, O, and F have very high electronegativities. H is fairly small, only 2.1. And as a result, there's a lot of polarity to the NH, OH, or FH bonds. And the combination of those two effects mean that those bonds are going to be extra polar, and extra strong dipole-dipole forces can form between molecules that have that kind of bonding in them. You may be aware of water having hydrogen bonding. That's one reason why water has an abnormally high boiling point of 100 degrees Celsius, whereas H2S and H2SE and H2TE show a general increase in boiling temperature as molecular weight increases. Water is out of sync with those three. It is very different, even though it has a much lower molecular weight of 18 grams per mole. It's got a much higher boiling point, and that's just due to the extra strong forces we see between water molecules called hydrogen bonding. HF also has that effect. It's not in line with HCl, HBr, and HI in the graph. And likewise, NH3 is not in line with the analogous three molecules, PH3, ASH3, and SBH3. CH4 is in line. CH4 doesn't have hydrogen bonding. So if we see CH4, it's where it should be in the graphs. Hydrogen bonding is very important if you study organic molecules, things like alcohols and amines and hydroxyl groups. Actually, hydroxyl would be alcohols. I meant to say carboxyl groups like carboxylic acids. These are all things that can have hydrogen bonds. Hydrogen bonds hold the DNA together along the connection between the two strands of DNA, as you see with guanine and cytosine having 3 hydrogen bonds, adenine and uracil having 3 hydrogen bonds. So that's how we can get the intermolecular forces in organics and in biology as well. Another type of intermolecular force is the intermolecular forces between nonpolar molecules. Noble gases can be liquids or solids at low enough temperatures, so there must be some kind of attraction between nonpolar molecules. The way we explain it is kind of a 3-step process. London said that first the nonpolar molecule just becomes temporarily imbalanced due to the movement of electrons. We call this an instantaneous dipole. Then that temporary dipole is going to polarize a nearby nonpolar molecule, creating an induced dipole. And then step 3 is going to be that the temporary dipole and the induced dipole will have an attractive force. These London dispersion forces do give the ability of every nonpolar molecule to form liquids, and most of them even can form solids if they get cold enough. There are 3 factors that can play into the strength of London dispersion forces. The first one is when the molecule is larger and has more electrons. We say it's more polarizable, and so its London dispersion forces will be stronger. In very large molecules like DNA or proteins, it could be that the London dispersion forces are stronger than the hydrogen bonds or the dipole-dipole forces, just because they're such large molecules. They have so many electrons that they're so polarizable. Also, shape plays into this. If you just look at the shape of the molecules and see do they match up as far as being able to have a lot of surface-to-surface contact in their shape, if that's true, you can expect your London dispersion forces to be greater. They can only attract if they are close. So what is their ability to get side by side and line up with each other in some kind of orientation that gives them a lot of surface-to-surface contact? And finally, pi bonds. Pi bonds are very polarizable, and so pi bonds can also, if you have some kind of pi bonding going on, that can actually strengthen the intermolecular forces. For example, benzene with its delocalized pi ring has very strong intermolecular forces due to its pi bonding. Ion dipole forces are another type of attraction that can occur between water and positive and negative ions. Down below you see the picture of water attracting to chloride and water attracting to sodium. It'd be very important to be able to draw those. Sometimes the AP test has you draw those, and it's important that you get the orientation of the water molecules correct, show the dotted lines between the waters and the ions, and also show that there will be multiple water molecules around a single ion. They call that the sphere of hydration when waters surround an ion in water. There's also a dipole-induced dipole where, for example, a water molecule, which is a dipole, it's a polar molecule, could actually polarize an oxygen, let's say, and that could create an attraction between oxygen and the water molecule. We'd say the oxygen is an induced dipole, the water is a permanent dipole. That attraction might help explain how oxygen, which is nonpolar, could dissolve in water, which is polar. We normally think like dissolves like, but in this case we do get some oxygen in water, and that is actually how fish can breathe by filtering out the oxygen, the O2 that's dissolved in water. Intermolecular forces actually very interesting here that could actually help us to distinguish between chemical and physical changes. If you think about it, most of our things we call physical changes are breaking and forming intermolecular forces. Melting, evaporation, these are actually breaking and forming intermolecular forces. We consider those to be physical changes. Chemical changes involve breaking and forming chemical bonds. For example, combustion of methane, you break the CH bonds and the O2 bonds, you form CO2 and water. You're breaking and forming chemical bonds, and that combustion of methane is definitely a chemical change. Now, if you go with this definition of physical and chemical change, now that you understand the difference between intermolecular forces and intramolecular forces, just be aware that there are some examples that are hard to define in this way. For example, I think up till now we would all agree that dissolving salt in water is a physical change. However, we do have ionic bonds in the salt being broken by the water molecules as they pull apart the ionic bonds using ion dipole forces between the ions in the water. So there's not just intermolecular forces like ion dipole forces involved here. There are chemical bonds, the ionic bonds in the salt, that are being broken. And so this is obviously a gray area. Would you consider dissolving salt in water to be chemical or physical? Okay. The attractive forces between molecules such as water can give rise to the liquid state. In the liquid state we have strong intermolecular forces between the particles. Some of the properties of liquids that can be tied directly to their intermolecular forces would be, first of all, the low compressibility because the molecules are attracted and very close together. Water and other liquids are not very compressible. Their lack of rigidity, in fact, their ability to not hold their shape, they take the shape of their container, they flow, all the things that a solid doesn't do. That lack of rigidity is simply due to the attractive forces being weaker than they are in a solid. Particles are close, they're attracted, but they can slide past each other. It can't hold a rigid shape. They have a higher density than gases. Once more, the packing is closer. They have boiling points and melting points that are closely linked to their attractive forces. Generally, if I say something has strong attractive forces, most of you would say that they have higher melting points and boiling points. Surface tension is another effect. The blue picture here in the middle shows the effect of surface tension. Because the particles in the middle of the liquid are attracted in all directions, but the particles on the surface are only attracted downward and left and right, there is no compensating upward force on the top layer of molecules in a liquid. As a result of that attraction downward that's not balanced by an attraction upward, the surface particles are pulled inward. And that basically has the effect of trying to minimize the surface area. If you think of a water droplet, it typically forms a sphere or tries to form a sphere, and that is actually the water particles on the surface being pulled inward, shaping it into a sphere. That surface tension does strengthen the bonds because it moves the molecules closer together, and as a result, that surface tension can be used by, say, a water spider to skitter across the top of the surface without falling into the water and being soaked. Vapor pressure is another factor that is affected by the strength of attractive forces. Typically, if the attractive forces are weak, it's easy for the liquid particles to escape to the vapor, and so you have a high vapor pressure. Viscosity, the resistance to flow. Something with strong intermolecular forces is going to resist flowing. It's going to try to hold its shape better. Things with weak intermolecular forces like gasoline is going to be low viscosity, and it's just going to be very thin and runny. Capillary action, we see in the lower left-hand corner here, the water molecules attempting to climb the glass on the sides of the test tube. That's called capillary action because of the strong attraction between the glass and the water. It actually distorts the surface of the liquid into a meniscus. The capillary action in a very thin tube will actually allow the water to climb the tube. In the bottom middle, we see that capillary action can actually allow water to move up a tube. In the very thin tubes in plants, water rises by capillary action, and that's how water gets up into a plant. Finally, we have the property that liquids can dissolve other substances. So it's not just particles of the liquid attracting other particles of the liquid. Particles of liquid can attract other substances. So water can dissolve salt, or water can dissolve alcohol. Finally, in the liquid state, there's actually a little more order than we may have previously thought. Some of the spectroscopic studies of liquids, some of the studies of liquid and its interaction with light show that liquids, in fact, do have more order than we thought previously. And so you could imagine it as, say, a water forming these small cages of water molecules, maybe 20 water molecules forming a type of a cage like an ice crystal, and then collapsing every few seconds. And so that could be an example of how that might happen. Moving into solids, we'll get back to liquids later, but moving into solids, there are two main kinds of solids: the amorphous solids, which have a considerable amount of disorder in their structure, and then the crystalline solids, which have a highly regular arrangement. Amorphous solids like glass tend to be clear. An amorphous plastic is a clear plastic, whereas a more crystalline plastic or crystalline solid like quartz will be more white in color and maybe block light instead of allowing light to pass through easily. So the amorphous structure allows light through more easily. Also, when an amorphous solid like glass breaks, you tend to get jagged edges instead of these nice flat crystal planes that you might get when you break a crystal like a diamond. You get a nice flat plane. Crystalline solids have a highly regular arrangement of the particles. The three-dimensional system of points that would represent the positions of the atoms or molecules or ions in a crystal is called the lattice structure, or the lattice points. A brick in the crystal structure, a single brick that repeats over and over again, is called a unit cell. So by studying the unit cell, we can get quite a bit of information about the entire crystal pattern. It's the repeating subunit of the crystal pattern. We study crystals using X-ray diffraction and something called the Bragg equation, which has to do with how light interacts with a crystal. That's enough for now. If you study deeper with some physics, maybe you'll get into X-ray diffraction and how X-ray diffraction can actually allow a chemist to understand the crystal structure by just looking at how X-rays interact with the crystal structure. Rosalind Franklin was actually able to determine the double helix of DNA using X-ray diffraction. Types of crystalline solids include ionic crystals, molecular crystals like ice, covalent networks like diamond, and metallic crystals like copper or iron. All of these things create these various crystalline forms. Molecular solids are typically going to have low melting points because their attractions are weak. Covalent networks are going to be very strong, like a diamond or silicon. Ionic solids are going to be strong but brittle. If you shift the position of the ions, they no longer attract and they might repel, and that can cause a crystal to shatter. And the metallic solids, because of their unique way of metallic bonding, are going to be malleable and ductile and also able to conduct electricity and heat. So getting into this metallic bonding, metals have high thermal and electrical conductivity. They're malleable and ductile. Their bonding is non-directional. They can bond in all directions, not just up, down, or in a 109.5 degree bond angle or whatever. They can bond to each other in all directions, and so the bonding is nothing like what we would consider covalent Vesper type bonding. Most metallic crystals have what we call a close packed arrangement. Majority of metals are going to be close packed. There are two main kinds of close packed arrangements: hexagonal close packed, which has an ABAB. The spheres from the top layer fit into the nest, into the open spaces between the spheres in the next layer down, and so forth on each layer down. If the number 1 layer and the number 3 layer are actually directly in line with each other, we consider that an ABAB, and that is called hexagonal close packed. The cubic close packed arrangement is actually ABC. So it's every third layer that's actually interlocked or in line with each other. Cubic close packed is actually identical to what we call face-centered cubic. Face-centered cubic shows 4 or 8 rather spheres at the corners of a cube, and then 6 spheres in the faces of a cube. So if we take the unit cell and sort of slice it, we see the picture on the right, which is called face-centered cubic. By using some of the dimensions of the atoms and the masses of the atoms, you can actually calculate the density. If you take one unit cell, figure out how many atoms are in that one unit cell, add up their masses, divide by the volume of the unit cell using the radius of the atoms to figure out the volume of the unit cell. You can divide the mass by the volume and get the density of the solid, because the density of one unit cell should be the density of the entire metal. The bonding model we use for metals is something called the electron C model, or the band model. In the electron C model, our valence electrons for the metals are able to move easily throughout the crystal and conduct electricity and carry energy in the form of heat. And so we have the explanation for the conductivity of metals from that. We also understand why metals with more valence electrons can be stronger. Group 2 metal, like the one we see here in letter B, has twice the valence electrons to hold the atoms together. The malleability of the metal. Since these electrons can flow, you can actually distort the shape and move the atoms around, and you will still have electrons between them, and they'll stay stuck together, and so you'll have metals able to change their shape. The band model is actually the idea of bonding and anti-bonding orbitals. In the case of metals, the bonding and antibonding orbitals energies overlap, and as a result, it's easy for an atom's electron to move to a nearby atom because there are empty orbitals in nearby atoms that have nearly identical energies to where they're coming from. And so electrons can just jump from atom to atom because of all the empty orbitals in the band of molecular orbitals that are found in a metal. We have two kinds of metal alloys. If the two atoms in the alloy have similar size, such as copper and zinc, you'll get a substitutional alloy. In the case of steel, where carbon is your alloy in alloyed atoms with iron, carbon's so much smaller it actually fits in the holes between the iron atoms, so we say it's interstitial. Those carbons in the holes actually help hold the layers together. They bond to multiple layers, and that's one reason why carbon makes iron stronger. Carbon and silicon are interesting because they're not metallically bonded. They are instead network atomic solids. They're not molecules, they're atoms, but they're atoms held together in large crystals by covalent bonds. In the case of diamond, carbon has sp3 hybrid orbitals and a covalent network that is tetrahedral. In the case of graphite, the carbon is sp2 hybridized and trigonal planar and makes these hexagons which stack on top of each other to create graphite. The hexagons have some delocalized pi orbitals which help to stick the layers together, but that's only an intermolecular force, and so the layers can slide, which makes graphite a good lubricant, and it also helps it slide off your pencil onto the paper when you write with a graphite pencil. The delocalized pi orbitals between the layers of graphite help explain why graphite is an electrical conductor, because electrons can flow through those delocalized pi orbitals. Silicon is considered a semiconductor. Silicon atoms in a crystal of silicon actually take on the same positions as they would in diamond. As a result, you have silicon with 4 valence electrons per atom. You actually fill up the bonding orbitals completely and nothing goes in the antibonding orbitals. The diagram below shows the band model for silicon. In the case of silicon at room temperature, most of your electrons are going to be in the lower area, which is called the valence band, and would only have to be excited to get up to the conduction band, or EC. That gap between them is called the band gap, and helps us understand how many electrons actually are capable of jumping that band gap to get up to the conduction band. So silicon in its very pure form is actually a very poor conductor. We call it a semiconductor, and that's simply because some of the electrons can jump to the conduction band. However, doping it with an atom from group 5 or group 3 can create a better position for movement of electrons. In the case of N-doped or group 5, you add an extra electron. Instead of having 4 electrons in a group 5 atom, you have 5 valence electrons. That 5th valence electron has to go to conduction band. Being in the conduction band, now all the other atoms have empty orbitals of that energy, and so that electron can move easily throughout the crystal. In the case of p-doped or a positive doped silicon, you have one missing electron because you have a group 3 atom. That missing electron creates a hole, and a hole is actually able to move throughout the crystal because if electrons go into the hole moves, and the hole is moving, so you're saying that a positive hole is moving, not a negative electron. But it can, in fact, move charge through the crystal that way. So you can dope it with p-doped or n-doped. If you put n-doped and p-doped side by side on a piece of silicon, you actually get what's called a p-n junction. A p-n junction makes a diode, which is a device that stops electrons from flowing in a particular direction. The way it does that is at the junction, the negative electrons from the N region are going to combine with the positive holes from the P region, and that's going to create a small voltage in that area because the electrons are going to migrate from the N region over to the P region, and that's going to create in that area a little bit of voltage. And if you try to come against that voltage and try to push electrons through the voltage, it will resist the flow of electrons. If you go with the voltage and bring electrons in from the other direction, it'll actually allow the electrons to flow. And so this voltage is actually going to try to oppose the voltage from one direction, but help the voltage from another direction. And that's why you can take, say, alternating current, which has flipping voltages, and convert it to direct current, because only one direction will be allowed through. So that's one way in which a p-n junction can be used. Molecular solids are going to have much weaker attractive forces between the particles than in a covalent network. Something like ice or sulfur or carbon dioxide would be a molecular solid. The molecules packed together in some kind of crystal arrangement to form a crystal of the solid, but the intermolecular forces are what's holding it together. So in the case of ice, the water molecules pack in fact, a less dense way than they pack in liquid water. So ice is less dense than water and floats on water. In sulfur, we have these S8 in the form of this puckered ring in the middle here, and then those puckered rings stack on top of each other to make the sulfur crystals. Carbon dioxide, you can see, lines up in kind of this staggered way to make a dry ice crystal. So molecular solids are going to be much softer and lower melting point than the other types of solids because of their weak intermolecular forces between them. Ionic solids are pretty strong. Ionic solids typically arrange in some kind of checkerboard type fashion with alternating positive cations and negative anions. One way in which they can do that is to consider the large anions in some kind of close packed arrangement, like face-centered cubic or hexagonal close packed or something like that, and then fit the smaller cations in the holes between them. Now there's actually three kinds of holes, varying in size from small to large. You would have a trigonal hole, where you just have three spheres side by side in a triangle. And then if you go down in between those three spheres, there's a small hole there called a trigonal hole. If you don't go all the way down in there, if you kind of sit up a little higher and sit under the atom from above, that's called a tetrahedral hole. That's a little more space. And then if you have a triangle of atoms that kind of staggers with a triangle below it, you can create what's called an octahedral hole, which is the largest space. So your typical ionic formulas are going to be based on, first of all, what is the size of the cation and the anion relative to each other, and also what is the ratio. Do we have a 1-to-1 ratio like sodium chloride, or do we have a 1-to-2 ratio like calcium chloride? If you analyze a unit cell for a crystal of an ionic solid, you can count the number of cations and anions in that unit cell, and you can decide what the chemical formula should be for that ionic solid. Getting back to liquids, and we can talk, and this can also be true for solids. Solids can also evaporate or sublimate. Vaporization or evaporation is when a liquid escapes to the vapor phase. If you keep a lid on the container, you create a evaporation condensation dynamic equilibrium after a period of time. You start out with only evaporation, and then as particles increase in number in the vapor phase, condensation increases. The energy it takes to vaporize is called the heat of vaporization, usually measured in kilojoules per mole. So we see the heat of vaporization for ammonia, benzene, ethanol, and others listed down below. Once you reach equilibrium, the pressure that vapor exerts, which should be constant if you keep the temperature constant, is called the equilibrium vapor pressure. Now that is that evaporation effect is caused by molecules at the surface having enough energy to overcome the intermolecular forces and escape. So if we take our Boltzmann distribution, which is in the middle here, we can see that only the particles that have that minimum escape energy are going to be the ones to escape. So that's a small fraction of the liquid particles in the vapor that are going to be able to escape to the vapor phase. The vapor pressure we see doesn't go up linearly with temperature. It actually goes up in a more exponential way. So if you take the natural log of the vapor pressure and graph it versus 1 over the temperature in kelvins, you get a straight line, and that's called the Clausius-Clapeyron equation or plot. And down below you can see the relationship between the natural log of the vapor pressure and the heat of vaporization divided by the gas constant times 1 over the temperature in kelvins plus a constant. And that in fact takes on the form of y equals mx plus b. That's why it's a linear plot there. If you take 2 points on that plot and do the math on finding the difference between the natural log of P2 and P1, you can get the equation here below, which says if you give me 1 vapor pressure, the heat of vaporization, and 2 temperatures, I can give you the other vapor pressure for the second temperature by using the Clausius-Clapeyron equation. Sublimation is simply when a solid evaporates. We don't call it evaporation, but it's the same basic thing, a vapor particle escaping from a solid. Solids have vapor pressure too. Changes of state can be plotted as a heating curve. We see the heating curve for a typical substance below. The temperature of the solid rises, levels off at the melting point, rises again, and then levels off at the boiling point, then rises again. We have these 5 different sections to that. We can calculate the energy for each of the transitions of temperature and state using the numbers on the right. So we'll practice some of those in class. Thinking of vapor pressure, when you have water and ice, below 0, water actually has a higher vapor pressure than ice. And so if we put water and ice in 2 compartments but let the vapor created by them exist, between them, what we would actually see is water with a higher vapor pressure. We would see the water molecules moving over to the solid side because the water molecules would have a higher tendency to escape. So what we would see is the water would move to the ice. That is called freezing, of course. At above 0 Celsius, they actually change places, and the ice has a higher vapor pressure than the water, and as a result we would see water from the ice side changing over to liquid water, and that would be melting. So that's kind of one way to understand melting. The normal melting point then would be when the vapor pressure of the solid is equal to that of the liquid. The normal boiling point is when the vapor pressure of the liquid is exactly 1 atmosphere, because that is the pressure which allows the bubble to push out against air pressure. Below that temperature, the normal boiling point, the vapor can't make a bubble because the bubbles just can't push against air pressure, pushing down on the surface of the liquid. So by analyzing vapor pressure curves, you can decide what temperature various liquids can boil at. You can also see that if you change the air pressure, say go up on a mountain, you'll actually change the boiling point. There are effects called supercooling and superheating. This is definitely seen in water. You can take water below its freezing point, and because it's difficult to form a crystal of ice in pure water, you can actually see water go below the freezing point and then rise back up to the freezing point as crystals begin to form. It's called supercooled water. Below its freezing point, it could still be liquid. You can also get water above its boiling point called superheated water. Sometimes that can happen in the microwave. You can heat water in a microwave and the water can still be liquid, but when the spoon is put in, bubbles form immediately, and somebody gets a steam burn or something from it. That's called superheated water. It's kind of similar to, if you remember from Chem 1, supersaturation, where the solubility effects allow you to have higher than saturation levels of crystals dissolved in water. One convenient way to represent the phases of a substance is using phase diagrams, which show the different phases that are stable at different temperatures and pressure. And so we see here that the solid state in gray, those are more stable at low temperatures and high pressures, whereas the vapor phase is more stable at high temperatures and low pressures, and the liquid phase is in the middle. Using some of these dotted lines, you can understand what would happen at these different conditions if you were to raise the temperature, say. So at, say, 4.58 torr, you would be ice until you get slightly above 0 Celsius. At that point A, all three phases could coexist. We call that the triple point. Above that temperature, you'd only have water vapor. At 1 atmosphere, which is the pressure we live at, you would have ice up to 0 Celsius, then it would transition to liquid, and then at C, at 100 Celsius, it would transition to a vapor. D is called the critical point. That is the point at which the pressure and temperature above that, you can only have what's called a supercritical fluid. The temperature is so high that you can't create strong enough attractive forces to hold it into a liquid state. But you can make it dense by putting it under pressure. It just won't liquefy because it just has too much kinetic energy. You can't get strong enough attractive forces to hold it in liquid state. One thing about the liquid and ice barrier or line between liquid and ice in water is it has a negative slope. And that actually allows us to understand that if you raise the pressure on ice, you can melt it. Carbon dioxide over on the right, we see that the triple point X is actually above 1 atmosphere. So you can have liquid carbon dioxide. But at 1 atmosphere, your solid carbon dioxide turns to a gas. That's a sublimation of dry ice at negative 78.5 Celsius. But at 5.11 atmospheres, you can have the beginnings of a liquid carbon dioxide. And above 5 atmospheres, you can have liquid carbon dioxide. So it is possible.